In the ancient world, the idea of something unbounded as a philosophical and metaphysical idea. Around the 4th century BC, ancient Indian texts like the Yajurveda explored the infinite. Concurrently, in Greece, the philosopher Zeno of Elea explored the concept using his famous paradoxes, like the arrow paradox, to show the physical limitations of dividing space and time infinitely. The earliest formal mathematical considerations of infinity as an actual calculable quantity date back to ancient Indian mathematicians. Bhaskara II, 1114 to 1185, and Brahmagupta, 598 to 668, were the first to state that dividing a number by 0 yields infinity, denoted as kahara. Bhaskara determined that adding or subtracting from infinity leaves it unchanged. In the 1870s, German mathematician Georg Cantor formulated the first rigorous modern mathematical theory of infinity. He proved that not all infinities are the same size, developing set theory to show that some infinite sets, like real numbers, are fundamentally larger than others, like whole numbers. Infinity is one of the most fascinating ideas in all of mathematics. Unlike ordinary numbers such as 1, 10, or even 1,000, infinity is not a finite number. Instead, infinity represents something that is unbounded, something that never comes to an end. One of the easiest ways to understand infinity is through the simple act of counting. 10, 11, 12, 13, 14, 15, and the process continues. Now, notice something remarkable. No matter how large a number becomes, we can always add 1 and obtain a larger number. This idea can also be visualized on a number line. As we move farther and farther to the right, the numbers continue without end. There is no final stopping point. No largest natural number exists. This endless counting process is what mathematicians mean when they say the natural numbers are infinite. The sequence never ends. And therefore, there are infinitely many natural numbers. Infinity is not a destination. It is the idea of continuing forever. Many important mathematical quantities are defined through infinite processes. One of the most beautiful examples is an infinite series. Consider the infinite sum. 1 plus 1/2 plus 1/4 plus 1/8, and so on forever. We begin with the number 1. Look at the partial sums. Adding 1/2 gives us 1.5. Adding 1/4 brings the total to 1 3/4. Adding 1/8 brings us even closer to 2. Notice what is happening geometrically. Each new term fills half of the previous amount. The pieces become smaller and smaller. Yet there are infinitely many of them. As more terms are added, the partial sums move closer and closer to 2. In fact, the infinite series converges exactly to 2. This remarkable result shows that infinitely many additions can produce a finite value. Infinity does not always mean something grows without bound. Infinity plays a fundamental role in calculus. One of its most important uses is in the concept of a limit. In calculus, infinity helps us describe quantities that grow without bound. Rather than representing a very large number, infinity often describes an endless process. To see this idea in action, let us examine a classic example from calculus. Let us see what happens as n becomes larger and larger. When n equals 5, 1 over n equals 0.2. When n equals 1,000, it shrinks to 0.001. Notice the pattern. As n grows larger, the value of 1 over n becomes smaller and smaller. The curve continually descends toward 0. Watch the moving point. As it travels farther to the right, the corresponding value of 1 over n moves closer and closer to 0. The values never increase. They continue to decrease as n grows. N never actually reaches infinity. Infinity is not a destination that n arrives at. Instead, infinity describes an endless process of growth. We imagine n becoming larger and larger without end, and we study how the expression behaves during that process. Therefore, the limit as n approaches infinity of 1 over n is 0. This beautiful example shows how calculus uses infinity to describe unending growth and the values that emerge from it. One of the most remarkable facts about infinity is that an infinite set can have exactly the same size as one of its proper subsets. At first, this sounds impossible. To understand why this is surprising, let us first look at a finite example. On the left, we have the set containing the elements 1 and 2. On the right, we have the larger set containing 1, 2, 3, 4, and 5. Clearly, the set on the right contains more elements. Obviously not equivalent. For finite sets, this is exactly what we expect. Now comes the surprising part. Infinity behaves very differently. On the left, we list the natural numbers. On the right, we list the even numbers. Notice that the even numbers form a proper subset of the natural numbers. Now watch the matching. Each natural number n is matched with the even number 2n. Every natural number has exactly one partner. And every even number has exactly one partner. So there is one-to-one correspondence, or the two sets are equivalent. They have the same cardinality, or size, even though one set is a proper subset of the other. This never happens for finite sets, but it does happen for infinite sets. And this is one of the fundamental characteristics of infinity. An infinite set can be put into one-to-one correspondence with a proper subset of itself. Imagine a hotel unlike any hotel in the real world. A hotel so large that it contains infinitely many rooms. Welcome to Hilbert's Hotel, one of the most famous thought experiments in mathematics. The hotel simply has room number 1, room number 2, room number 3, and so on forever. The rooms never end. Every room is occupied. In an ordinary hotel, this would mean there is no space left. But suddenly, a new guest arrives and asks for a room. The manager comes up with a remarkable plan. Ask the guest in room 1 to move to room 2. Ask the guest in room 2 to move to room 3, and so on. Every guest moves exactly one room forward. Because there are infinitely many rooms, there is always a next room available. And now, something extraordinary happens. Room number 1 becomes empty. A room has appeared out of a completely full hotel. The new guest can now move into room 1. The hotel remains full, and yet it has successfully accommodated one more guest. This would be impossible in any finite hotel. A hotel with 100 occupied rooms cannot suddenly create room for another guest. But infinity plays by different rules. Hilbert's Hotel reveals one of the deepest ideas in mathematics. An infinite collection can behave in ways that seem impossible from a finite perspective. Infinity is not simply a very large number. It is a fundamentally different kind of mathematical object. A full, infinite hotel can still make room for more. And that is one of the beautiful mysteries of infinity.